Good afternoon, everyone. It's a real honor to join this seminar series. As I was looking at the previous speakers, this is really a prestigious group, and I feel really honored to have been invited by the Atoms group, and I really thank you very much for this opportunity. What I really want to do today is share with you some lessons I've learned doing gas hydrates research, and I intentionally selected the term laboratory trials, which I've adopted from the work on pulp and paper technology that is being used really to demonstrate the fact that while you're working in the lab, you're using fluids which represent as much as possible the industrial situation. My first contact with gas hydrates has been many years ago. I think it was exactly 37 years ago. I was taking a graduate course from Bob Heidemann at the University of Calgary, and one of the exercises I had to do was to calculate the partial molar volume of water into the hydrate. I hope you're all listening well. Is my sound clear?
Yes.
Thank you.
You should start sharing your presentation too, please.
Hello.
Is it? Oh, okay. Let me share. Sorry,
Yeah, it's fine.
I had to. Okay. I hope now you can see my slide.
Yeah, it's great.
Okay.
Yes.
So as I mentioned, my goal is to share some lessons I've learned over the years in doing gas hydrates research, and let's get started. So the question that has been in my mind, particularly when we were doing work with inhibitors, is how really can you bridge the gap between what you're doing in the lab and the performance in the field, whether you want to test chemicals in the field or you want to develop a process to extract natural gas from hydrates. And again, I've adopted this from the pulp and paper field, where I've been doing work in colloid chemistry, where we're doing the chemical trials in the lab of particularly specialized flocculants and agglomerates, and then we wanted to test them in the field, but the field testing is quite expensive. You cannot stop a paper machine. So you had to really think very carefully about your laboratory trials. So, and I guess the same challenge is faced with gas hydrates. So how do you actually build the bridge between laboratory investigations and field performance so you can safely cross that bridge? So the outline of my talk is as follows. I want to just give a brief introduction to gas or clathrate hydrates, assuming that you have some knowledge of this interdisciplinary field. And I'm going to focus on two aspects of gas hydrates. One is the use of green inhibitors in the oil and gas industry to make sure that hydrocarbon fluids flow without creating problems due to hydrate formation. And the second aspect is related to the extraction of natural gas from the Earth's gas hydrates. It's an unconventional form of natural gas. So very briefly, gas hydrates are what we call inclusion type crystals, which can easily form in the laboratory and have been formed in the literature. I have some pictures here of hydrates that we formed in the lab. On the left, this is a high pressure vessel with marine type windows that allow you to watch inside how CO2 and water at these conditions can form hydrate. It's been known for many years, since 1882, that CO2 forms a hydrate. I'm not sure why it... on the right, we've exposed water droplets to methane and propane gas, and that formed the crystal underneath. Below, you can see this is a picture from Roppel and Kessler in a paper 5 years ago that shows this white material here, which is gas hydrate, beneath this muscle-coated carbonate rock. That's in the seafloor on the Gulf of Mexico. And on the left, it's a remarkable gas hydrate that was identified about 18 years ago. This is off the coast of Vancouver Island in Canada. What was fascinating about is we know that the majority of these hydrates in the earth are methane hydrates. However, this one here off the coast of Vancouver Island, it turns out to be a hydrate that contains about 13 different chemicals, mostly hydrocarbons and predominantly methane, but it does contain some larger molecules, and it is indeed structure H hydrate. One of the most remarkable aspects of gas hydrates is the tremendous concentration of the gas in the hydrate. And just look at the mole fraction of CO2 and methane in water. It's in the order of 10 to the minus 4 and 10 to the minus 5. And yet in the hydrate phase, it's almost, it's 14%, closely to 14%. So it's a remarkable concentration of gas molecules in the hydrate solid phase. The best way to look at hydrates is by invoking the Roman god Janus. This is a double-faced god, and some of you may be familiar with the Janus particles in the field of colloid science, where you have half the particle having hydrophilic and the other half being hydrophobic. And I like to look at hydrates from the similar lens, because on my left, I can see hydrates as being a problem, and that has created the need for finding ways to prevent the plugging of oil and gas pipelines. And that's been a problem with us since the 1930s, and it's still with us a challenge as we move into more offshore production and more challenging production and processing locations. It can be a problem also in continental slopes, where the decomposition can fluidize the slope and create unstable conditions. And lastly, it can create a runaway greenhouse effect. As a result of current global warming, methane in the earth can begin being released in the atmosphere. On the other hand, it's an opportunity, and we can look at hydrates in the earth as a potential source of natural gas. We've been looking at ways of taking advantage of that tremendous concentration of gases in the hydrate phase for natural gas storage or CO2 capture and storage, and other opportunities. So let me begin by talking about the lessons we learned from working in the flow assurance issue. Basically, when you take hydrocarbon fluids to a central processing facility along this pathway, you have hydrocarbon and water, and you may encounter thermodynamic conditions that's illustrated better here on this pressure temperature diagram. You may encounter conditions inside the hydrate stable region. And the traditional way of dealing with this is to inject methanol or other thermodynamic inhibitors. That can be costly and also create some issues downstream of environmental nature. So in the last 25 years, people have looked at a different way of injecting rather small concentration of water-soluble polymers, which either delay the onset of hydrate formation, or in case hydrates form, they create an environment where the hydrate particles remain dispersed, and therefore the fluids keep flowing as a slurry. So the motivation for our work goes back to the hydrate conference in Vancouver in 2008, One of the keynote speeches was by Alfred Klom, who has been working on the issue of those kinetic inhibitors, as we call them, for quite some time. And he stated that one may also think that there exist laboratory experiments and procedures, the results of which can unambiguously be transferred or translated into the performance of an LDHI, a low dosage hydrate inhibitor in the field. Here it is argued that this may not be so. So this prompted us to look into this issue, and we said two research objectives. First, to identify green or environmentally accepted low dosage hydrate inhibitors. Chemical inhibitors are not preferred because the monomer can be environmentally challenging. So the hypothesis we pursued was that macromolecules that had evolved in certain overwintering organisms to absorb and restrict ice crystal growth and thereby protect them from cellular damage might also be useful as low dosage hydrate inhibitors. And we've collaborated with John Ripmister at NRC and Virginia Walker, a biologist at Queen's University, as well as Saman Alavi at Ottawa, and a rheologist here at UBC. And you'll see why we had to assemble this team. And the second objective was, again, focusing on how to bridge the gap between lab and the field. So when you look at hydrate formation in the field, you have to assemble a wealth of information trying to understand the system. You have to look at the chemistry of fluids, what kind of hydrocarbons, what kind of dissolved or suspended material we have there. There might be naturally occurring substances in oil that inhibit or enhance hydrate formation. You might have a material that you don't expect it to be there. The hydrodynamic conditions play a key role in the dynamics of hydrate formation dissociation. There might be other reasons that you don't know. So you're dealing with a very complex system in the field. And when you go into the lab, you have to try and map as many of these factors as possible. Now, the other aspect about hydrates is that we're looking at them at different length and time scales. So if you're interested in mechanisms, you're looking really at a very small length and time scale. You look at structures, etc. But when you go into technology, whether it is inhibition in pipelines or gas extraction, we're talking now about reservoir size points of interest and really large time scales. And in between, you have macroscopic experiments that you do with packed beds of sediment particles, or you do morphology experiments with droplets as small as a few milliliters and so on. So you have to then keep in mind that this tremendous variation in length and time scales. So we thought that we need to come up with a rather systematic approach. In other words, not just apply what we know, let's say you're a thermodynamicist, you look at the thermodynamic aspects. You're a rheologist, you look at rheology. Let's assemble what we need and take a holistic approach. And the best way to represent this is to follow what we call a multi-scale approach. That is, do things that look at hydrates at the different time and length scales. And also look at the complexity of the fluids we're dealing with, and also incorporate potential surface effects. So this means that we assemble a number of tools, all the way from XRD, Raman, NMR, calorimetry, rheology. Morphology is an interesting approach that was pioneered by Professor Yasuhiko Mori at Keio University in Japan, where I was in sabbatical about 20 plus years ago. And it's a powerful technique because you can set up different systems and look at how crystals grow at different interfaces, etc. And we've done most of the work in stirred autoclaves and fixed bed reactors. And in terms of the complexity, you look at gas mixtures, you look at the effect of salinity, you look at the presence of a liquid, another liquid phase, predominantly hydrocarbon. And you look at pipeline wall interactions, where the surface energy of those walls. And you add into the mixture the simulations, which give you the opportunity to look at conditions you cannot easily access into the laboratory. So we've tried to follow this approach and try and understand the system then in a way that represents the reality in the field as best as possible, and that perhaps justifies the term laboratory trial more clearly. So the work that we've done, we've clearly shown that there are green inhibitors in the form of antifreeze proteins, and they have some interesting behavior. The antifreeze protein, they have a single hydrate peak, as opposed to multiple hydrate melting peaks that we observe with chemical inhibitors. We use PVP, PVCAP, and a commercial one. And the other thing that we've observed, and it has implications in the field, is that in the presence of AFPs, the hydrates decompose faster and completely and at a lower temperature. And that has been summarized in an article in the Canadian Journal of Chemistry. This issue of the difference between the chemical inhibitors, as I mentioned, has implications, because while chemical inhibitors may be more, and they are in general, more effective at inhibiting hydrate formation, in conditions under which reformation of hydrates is likely, then the elevated stability of the formed hydrates and the presence of multiple melting peaks may make the use of those chemical inhibitors more challenging in the field. It was also interesting to look at the surface effects, and this is something that was brought to my attention a long time ago by a professor at Caltech. His name was William North, who was looking at hydrates from an environmental standpoint. They were doing experiments with hydrophobic containers, and indeed they noticed an effect. It was published at a report to EPRI back then, and we did look at this more systematically, and we found that if you coat a reactor with a hydrophobic substance, you really observe a sizable, statistically significant delay in nucleation. And therefore, you have a very effective system by combining a hydrophobic coated system with some inhibition. It becomes a powerful synergy. Now let's look at some more observations based on this multi-scale approach and see one has to be careful to interpret these, to look at these data. So what I'm showing you here is what we call the induction time. Induction time is the time it takes for the onset of hydrate formation. And what we're looking here is the induction times in an autoclave, in a differential scanning calorimeter, high pressure calorimeter, and in a high pressure rheometer. So for each system, there is 3 times. And you see that the induction times are different, even though the same chemical system is being used. And that is what you normally expect. Hydrate formation is a stochastic event, and it's not surprising to see these differences. What was rewarding, however, to see that the qualitative the results, they do follow a trend. That is, if you include PV-CAP, which is a chemical inhibitor, PVP, it's another chemical inhibitor, not as strong as PV-CAP. If you add C7, a hydrocarbon liquid phase, and then PV-CAP and PVP, you notice that the trends are consistent. That is, the induction time in the presence of PV-CAP is longer in every system and follows the same trend. So that gives you, I believe, more confidence into the impact of the chemical, because with 3 independent methods, although you've got different induction times, you've got the same trend in terms of the activity of the chemical. Now, there are complications, and you can have a situation that you observe what we would call catastrophic hydrate growth. And you don't always observe that. You don't observe that in every system. This is a very simple static system, and you can see how hydrate grew to an extent that covered the whole thing, the whole beaker there. And this is something we've observed time and again, and we published a few papers on this. And we believe that although this has been identified, at least to the best of our knowledge, in the laboratory, there's nothing that says that that could not happen in a field situation. Again, this is a result of using a low dosage inhibitor. As I mentioned, you want to use them to delay the onset of hydrate nucleation. That happens. But once hydrates form, you want, in a system, you want them to be controlled. But indeed, you have the opposite. You have catastrophic growth here. And I think what happens, based on work that was done also in Japan by Professor Mori, what we believe happens is that the presence of the inhibitor alters the morphology of the hydrate and creates capillary pathways for water to move through and go and meet the gas, and this way hydrate formation is promoted. And we try to quantify this phenomenon and assess the risk. So we've introduced the term hydrate catastrophic index. Oops. Based on the different experiments that we've been doing, whether you do rheology or calorimeter, you can define, you can select a parameter, the rate of growth, for example, with the LDHI and without. And once this value is greater than 1, then you have a risk for the formation of hydrates at an accelerated pace that results in complete and hydrate plugging. And so this gives you the opportunity to use the laboratory trials from different settings and assess the potential for catastrophic growth when using a particular low dosage hydrate inhibitor, chemical or AFP. So the other we had to ask is, what is the mechanism by which these AFPs really interact with the hydrate surface? We know that they give the opportunity in fish or other organisms to survive harsh winter by blocking ice crystal growth and preventing cellular damage. And then the question is, how do they interact with the hydrate? So let me just, so we looked at the winter flounder antifreeze protein that is shown here in figure 1. It has 2 residues, a threonine residue that has an OH and a CH3 group, and the alanine residue, which has just a methyl group, CH3. And you can see here in the structure, you see the 4 threonine residues, and the arrow showing the alanine residues at if the threonine is at position I, then the alanine is at position I+4 and I+7. And it is these residues that interact with the hydrate surface. It was thought that the inhibition of ice was due to hydrogen bonding because of this OH. But it was actually shown by mutating the protein and creating one without OH that the hydrogen bonding plays really a minor role, and it is an adsorption which is between the ice binding surface of the protein and the ice itself, not hydrogen bonding, just an adsorption interaction. And in terms, and with respect to hydrate, the hydrate has less welcoming surfaces. But if you look at, we've looked at the surface 100 and 00 at the 001 plane, and it has, what happens with that plane, it has some half empty cages, which is where the growth is going to happen by incorporating methane molecules. So Alireza Bakirzadeh did some molecular dynamic simulations, and which we thought at the time were the first that were done with methane and antifreeze proteins. And really and there is this video which I'm going to try and play, but let me see if it will play. Sorry, there's an advertisement. I will skip it. So you can see the pendant methyl group inside this half empty cage. So this is what happens. The presence of antifreeze protein somehow deceives the growing hydrate crystal, and it prevents the transfer of the mass transfer of water and methane molecules to the growing hydrate cells. And we believe that's the blocking mechanism by which the antifreeze protein does inhibit hydrate formation. And this is also shown here in this image, where is the methyl pendant group inside the half empty cage. We use this F3 parameter to track the state of water, this is all summarized in a paper a few years ago. That was quite revealing because it really showed that it was a cooperative binding between the methyl groups primarily and the hydrate empty cages that was responsible for the inhibition, that the hydrogen bonding plays a rather minor role in this situation. One may then engineer inhibitors to take advantage of this fact. So let me summarize this part of the talk by saying that antifreeze proteins are proven green gas hydrate inhibitors, and they may have some practical advantages versus the chemical inhibitors such as PVCAP, etc., although they're not as strong in terms of the inhibiting action. The lesson we've learned is that you need to be aware of the potential for hydrate catastrophic growth, and really to understand your system in a more confident and be more confident about its behavior is to assemble a toolkit that looks at the different aspects and different settings of hydrates. And this reminds me of what a famous thermodynamicist from MIT, John Keenan, in the 50s said about the difference between applied science and engineering, that in engineering you assemble the tools to solve the problem rather than the other way, trying to find a problem and apply your toolkit. I paraphrased it a bit, but the point is you need to assemble a variety of tools that take advantage of the fact that hydrates really need to be studied at different time and length scales to be understood better. Let me now switch to energy from the Earth's gas hydrates. And the question we posed really is, when you are into the laboratory, does the sample size matter? And one might say, of course it does. Well, let's see, what does that mean? And how really can you generalize results from the laboratory if you want to take those results and do reservoir simulation to assess the performance of a hydrate reservoir? Just very briefly about this vast topic, there is now well known that there's widespread occurrence of gas hydrate deposits in almost every corner of the world. Hydrates are more democratic than oil. Oil has concentrated in the Middle East and some bit in North America and Russia, but many parts of the world don't have oil and natural gas. Hydrates are almost everywhere. And the estimates of the amount of gas hydrates vary considerably, okay? But extensive research work and field work over the years has identified those sediments that are sand-rich as having the greatest potential to be exploited. And just a few numbers about the resource potential. If you look at all the estimates, there's a mean value of about 20,000 trillion cubic meters. That's a huge number. Think about that the conventional natural gas in the world is 370 TCM. And we consume about 1 TCM every 5 months. Some more recent estimates, and I have the literature here, I believe, yes, it's from Boswell and Collet. It's in the Gulf of Mexico, it may contain about 600 TCM with 190 in sand reservoirs, which means it can be exploited. And in the North Slope of Alaska, there's been a lot of field work there. It's estimated that the technically recoverable gas would be about 54 trillion cubic feet. 35 trillion cubic feet is 1 TCM. The depressurization, whereby you induce a pressure reduction that shifts the hydrate stability to the pressure temperature conditions that the hydrate is not viable anymore. And that has proven to be the most viable production technology. The key is to demonstrate sustainable production rate over a long period of time. If you look at 2 most recent tests in Japan and China, they sustained production for about 8 or 6 days. Okay, so the key focus right now is to do field tests and attempt a longer duration. Now, on the question that I posed about the sample size, if you look at some prior work, Paul Handa was a calorimeter person at the National Research Council and one of those early workers on hydrates since the 80s. In a study he published in 88, he said it was found that when a finely powdered sample was heated from 80 Kelvin, it released all of its gas below 273 K and thus underwent a one-step dissociation process. However, if the hydrate was in the form of large crystals, then it released a major part of the enclathrated gas below 273 and the remaining above 273, and thus underwent a 2-step dissociation process. A more recent paper by McCallum looked at a large hydrate forming reactor, 72 liters, as well as a small power reactor, and state that the likelihood of hydrate nucleation is increased in the larger vessel. That means the induction time is shorter. So the way to address this question, we thought, is to look at a fixed bed of sand particles, and we chose sand particles because that's a national environment of practical interest. Excuse me. And what we did is, this is the crystallizer, and we've modified it to have 3 samples by just inserting copper cylinders inside so that we can reduce the active size. Okay, so you can see, so you have the original volume of the reactor. You have another volume by inserting a copper cylinder, and we selected copper for heat transfer reasons, so that heat is transferred effectively. And this way we've created 3 bed sizes. We call them crystallizer without any copper cylinder, crystallizer plus copper cylinder 1, and crystallizer plus copper cylinder 1 and copper cylinder 2. And these are the volumes and the mass of the bed. Now, if you look at then, and we've placed many thermocouples inside, so that we can have a good understanding of the temperature. Temperature is a nice signature for hydrate nucleation, because hydrate formation releases heat, and you can then identify the points of hydrate nucleation. So what we've seen by plotting temperature versus time for all these 6 thermocouples, we see different behavior. At the beginning, we see nucleation taking place at many parts, and that's where you see the different peaks there. So nucleation is not an event in one place, okay? It occurs in more than one place in the bed. And as you go along, you see smaller nucleation events at different times. And you achieve a conversion of water of about 78.5% of the water present has been converted to hydrate. So we looked at the literature, and Motrakovsky, who has been doing a lot of NMR work at NRC, has stated that in quiescent systems, the stochastic nature of hydrate nucleation prevails. If you're doing experiments in bulk system, you have one single nucleation event, because what you're actually doing is you're monitoring an averaging process that takes place in a stirred vessel, for example. But that doesn't give you the holistic picture in terms of hydrate growth. Now, interestingly, at two temperatures, 4 degrees and 1 degree, we've observed this phenomenon of multiple points of nucleation in space and time. But if you go to a higher temperature, you only observe one nucleation event. And if you look at the rate of moles consumed, you can verify that the driving force is not as high here. Okay, so it's not. So the multiplicity does not necessarily always occur. It depends also on the driving force. Now, we've also looked at a totally different experiment that was done in Ottawa using the NMR facilities there. Again, a fixed bed of sand particles with different particle size and different water content. And we probe this with NMR, where you can see, which confirm the purple places here so hydrate, which confirm the multiplicity of nucleation at different points in time and space. So that's in agreement with the observations we made in experiments here in Vancouver with a different hydrate bed. What was interesting in this one is that we also monitor the pressure drop, and so that which you can convert into normalized uptake curve, and you can see this is a smooth kind of curve. It doesn't show the heterogeneity because it really represents averaging over many local environments. So if you're looking to model hydrates with gas uptake curve, which is the normal approach when we do stirred vessel type experiments, it is not necessarily representative of what would happen in a situation where there is multiplicity of nucleation and growth. So if we want to summarize, the formation porous media, especially in homogeneous, and in fact, we saw that the hydrate formation can be grouped into a three-stage process once you have this multiplicity. And if you want to link the lab with the field, you have to think that although the gas uptake curve, which we normally consider to correlate with hydro growth, shows uniform behavior, this is just a result of averaging over many hydrate formation locations in a bed. And therefore, the postulated sequence induction time, nucleation, growth for modeling is not necessarily valid when you're looking at hydrate formation in porous media. We looked then at hydrate dissociation, and we looked at thermally stimulating a hydrate by moving into the unstable regime. The delta T is the sort of the driving force. And then we started grouping the data in terms of the driving force, 10 and 4 degrees C. And then by looking at data with the same driving force, but different bed size, we could see that in all cases, we see a two-step process, which can be correlated quite well. These two-stage process is interesting that the stage one process depends on the size of the bend, as you can see, but the second stage becomes independent of the bed size. Okay. So the size matters with respect to the early stages of dissociation. We then did the same, but with depressurization. And in this case, again, you start with hydrate and you begin dropping the pressure by creating a delta P below the equilibrium pressure. And you group the data then, and then in terms of the recovery percent of methane. And what we've seen is that we can actually correlate all these curves with one parameter. And we can look at the recovery, the percent recovery of methane from the bed versus time versus the equilibrium or the steady state. Just one time constant, and that time constant actually correlates linearly with the bed volume. And the initial stage, again, strongly depends on the bed size. There's a three-step process. So the surprising thing is that just a very simple equation with one parameter that correlates with the bed size can actually model the results for depressurization. So we concluded that the size of the lab sample matters in hydrate formation dissociation. Therefore, the lesson is that if you use, if you want to compare models with experimental data, you need to make sure you're using different sample sizes. More importantly, and this happens a lot, when you take samples of naturally occurring hydrates and you take them into the lab for physical testing, we think that it's important to use different sample sizes to measure the rate of gas release. And that is quite critical, I think, to happen, because we do take these high pressure samples and bring them into the lab for analysis. Now, interesting, another aspect of linear lab modeling with field application is the issue here that was reported in Scientific American from Shoes, a geochemist. The presence of bubbles, lens-shaped bubbles, once you decompose hydrates in a reservoir. And we actually did that, did molecular simulations by looking at hydrate enclosed in a silica surrounded by two silica plates and water on both sides, or two silica plates with a water layer in a thin water layer in between. And we tracked the evolution of methane gas from hydrate, and we noticed that it tends to the methane molecules tend to aggregate and create these nanobubbles, which was quite interesting. So let me then come to an end and by reminding the question that I posed at the beginning on how to bridge the gap with field performance. And what we've learned was that by taking advantage of the fact that hydrates are really an opportunity to look at them at different length and time scales, gave us the ability to create a multi-scale approach, which when we indeed followed, made us aware of the presence of the ability of LDHIs to exploit situations and create conditions of hydrate catastrophic growth by really creating the morphology of hydrate in such a way that there are capillary pathways that enhance the contact of water with the gas. We were able to, through simulations, to locate nanobubbles formed during hydrate dissociation. We are convinced that the sample in the laboratory matters, especially if you wish to model hydrate formation or do numerical simulations. And more importantly, we think when you take samples from the field to bring them to the lab, and you want to check the rate of gas release and then use it for modeling, the size of the sample does matter. So we hope that the lessons we've learned over the years could be useful, particularly for those who are working in the laboratory. And with this, I'd like to thank you for your attention. And I'd like to invite you to Vancouver. We have the Canadian Chemical Engineering Conference in October. It's going to be in person for the first time after 2 years. And this is a nice picture from Vancouver. So I'd like to thank you again for the opportunity to be with you today.
Dr. Peter Englezos, thank you so much for your presentation. We're now open to questions. If someone wants to participate, please enable your microphone or write it down in the chat and we will read it. Also, our YouTube viewers can write it down too, of course.
Can I start?
For sure, Professor.
Thank you, Peter, for the presentation. Very interesting. I wonder, in the experimental measurement for induction time, you use calorimetry and a rheometer. Normally, well, for induction time, the particle is really small, maybe, if the driving force not so strong. Or indeed, if the driving force is strong, the size of the particle is very, very small. Can you see this initial size using calorimetry and rheometer? Or,
yes.
or you are measuring something much bigger than the induction time?
Yeah, we've in both cases we've published the sample holder and we've given a picture and a description of the dimensions of the sample holder. The samples in the calorimeter are quite small. I forget the exact volume, but they're good enough because this high pressure calorimeter is quite sensitive, and you can obviously calibrate it against known specimens. With the rheometry, it's really macroscopic, the experiment, and what happens is the apparent viscosity shoots up once you have hydrate crystals, and you have to be really careful and stop it. You don't want to damage the rheometer. So we didn't have a problem with actually getting a signal.
Okay.
And of course, if you do NMR, then you are tracking the protons and you can see it very clearly.
Yeah, with NMR, I have no doubt about. But
anyway, the answer to your question is that we did not have a problem with the sample sizes we used, and in both cases, in rheology and in calorimeter. The details, the experimental details are available in the literature.
Thank you, Peter. The other point is the picture that you have shown us about the interface between hydrate and protein solution. Can you put again this picture for us?
Okay, let me.
My wonder is normally we expect some thin layers at the interface that maybe play as an important role in this absorption for protein in the surface. But I don't know if you saw that in your simulation.
Could you, sorry, Fred, could you repeat the question?
No, what to expect sometimes is at the interface, it forms a very thin layers of water-like. It's not exactly the water structure, not exactly the solid structure, but a thin layers of water that maybe plays an important role in the properties at the interface.
Yeah, we track this with the F3. We use this parameter F3 to track the state of water around. So when this parameter value has, and we postulate, let me see the numbers here. We postulate a value of 0.015 that corresponds to water molecules arranged in a hydrate-like environment, and a value of 0.09 corresponds to liquid water. So we do track the structuring of the water environment in all simulations by following this order parameter, F3 order parameter.
Thank you, Peter.
Yeah.
Thank you.
Now, Professor Richard has raised his hand. So please, Professor Richard.
Okay, so I had a question about whether you'd be interested in instead of a fixed bed, a bed in which the fluid is flowing through the bed. Wouldn't that be more realistic?
If the induction time is an hour, you need a long bed. You need a pipeline. You're talking about a pipeline type of reactor.
Well, so I was wondering.
And there are pipeline reactors, the so-called hydrate flow loops that Exxon and the University of Tulsa has, but they're not beds of particles. They're just they just flow fluids. There's no suspended. There's no particles there. So it's not. People tried a fluidized bed, a high pressure fluidized bed reactor. That didn't go far. I don't know why.
So there's another reactor that maybe this is totally off base, but I worked with this guy many years ago. His name was Berty, B-E-R-T-Y. Have you ever heard of the Berty reactor?
Sorry, can you say the name again?
Berty, B-E-R-T-Y.
Doesn't ring a bell right now.
So he worked with Union Carbide for many years, and they used this reactor to study catalysts. Most studies of catalysts were restricted to just the initial conversion. So you fed in a feed that was totally unconverted, and then you could measure how much got converted just based on that initial conversion. And then that was a problem because in industry, you want to go to much higher conversions. Okay. And so what he came up with is it's still an autoclave. It has a magnetic impeller at the bottom, and then it has the porous bed in a kind of a toroidal, in the center of a toroid, so that the flow goes through the bed. So in terms of the amount of conversion, it looks like a CSTR, but you know the rate of flow through the bed and the number of passes per minute. And so you can convert that into an actual flow through the bed.
I see. So the fluids are circulating.
Yes, the fluid
Okay.
is circulating, but in a fixed way instead of a slurry or
Yeah. I'm not aware of anybody having done that. That's true. There have been some innovative designs that come out of China. And I think I understand the concept you're talking about. I haven't seen it in the hydrate context. So.
There was a time when you could buy those
Oh.
Berti reactors off the shelf.
Okay, I took a note here to look into this.
Yeah, I think it might be interesting for you. I don't know if it's, I'm not sure I fully understand everything here, but if that's interesting.
That reconfiguration might be of interest if you're looking at applications where you need to convert to enhance the conversion. Again, same motivation like the catalyst version, particularly in areas of CO2 capture or storage of natural gas. Yeah, that might be of interest in those applications.
Okay, yeah, let me know how it turns out, if there's anything interesting that happens.
I'll keep you in touch. And by the way, are you planning another edition of your thermo book? I'm using it for my third year class.
Yeah, we're planning a third edition, and the third edition we have approval. This won't help you, but this audience might be interested. We have approval for translation into Spanish and Portuguese, actually.
Okay.
So that'll be a part of the third edition. That'll be probably about a few years from now. So 3 to 5 years from now, though.
Okay. Thank you.
But the properties of gases and liquids should be out by September this year. And there'll be interesting results in there that pertain to the second edition, because we included coverage of the CosmoRS methods. And in PGL, I bring out a little bit more about how those methods relate to the SAFT methods. And so the PGL will be a nice complement in the meantime before the third edition comes out.
Great. Look forward to it.
Okay.
Okay, so does anyone want to ask another question?
I just want to say thank Fred, because he looked at the Van der Waals plateau model and published a nice review recently. Jerry Holder in the 80s told me every graduate student who starts working on hydrates has to read the Van der Waals plateau paper a few times over if you really want to understand hydrate. It's a remarkable achievement, this Van der Waals plateau model, but it's nice to see people like Fred are taking a fresh look at it. You're mute, Fred.
Amadeu Sun is here. He's also co-author for this review, and he helps us a lot with this. But I think he left.
He knows all about hydrates.
Yeah. Thank you, Peter.
Okay, so our time is almost over. I want to thank you everyone for this discussion. And once again, thank you, Professor Peter, for the presentation.